So the one type of differential equation that we are going to learn to solve is called a separable equation. And separable equations always have a specific format. They do not have to be linear. They can be, but they don't have to be. They're typically order 1. And we can solve these equations with math that we already know. So we really don't have to learn any new calculus in order to do this. So it's just like it sounds. These equations, we're going to be able to separate something. So there's a specific format that we're going to look for that's going to tell us we have a separable equation. So a differential equation is separable if it can be written in the form dy dx equals f of x times g of y. So if we can isolate the dy dx on the left side of the equation, and when we do that, it's possible to get the right-hand side of the equation written as a product of a function of x's and a function of y's, then it's a separable equation. Many of the equations that we're going to work on will already be in this form. Some other ones, we might have to move some terms around in order to get it in this form. So once we determine that our equation is separable, what we're going to do is we're going to separate the x's and the y's. And I keep using x and y, but really you could have any dependent and independent variables there. But it's important to know the difference. When you look at your derivative, the dependent variable is always in the top. Because technically what dy dx is saying is that we're taking the derivative of y, of an equation named y, with respect to x. That means I'm going through my y equation and I'm taking the derivative of all the x's. So on the top, the y is like the name of the equation, and on the bottom, it tells us what our independent variable is. It's important to know this because we always want our answer, if possible, we want our answer solved for the dependent variable. I want to be able to say my solution is y equals, and then my function. So if we were to mix up the variables here and use like s and t, and it said ds dt, whatever's on the top would be the dependent, whatever's on the bottom is the independent, and ultimately we're trying to solve for the dependent, whatever's in the top. So that's an important thing to understand as well. So the way that we separate the x's and the y's is we're going to multiply the dx over. So we're actually going to separate this, this differential notation here, the dy and the dx. We're going to multiply the dx over to the right side, And we're going to divide the g of y over to the left-hand side. Now I'm saying divide because right now I have it written as a product. It's possible that this is going to be written a little bit differently, and in order to separate them I might have to do some different operations. It will always be either multiplication or division though. But like we said at the beginning of this section, really multiplication and division are the same thing. Multiplying is the same as dividing by the reciprocal. So if I do this, I'll end up with 1 over g of y dy equals f of x dx. So everything with a y is on the left, everything with an x is on the right. Now, what have we learned how to do throughout calculus that has this little dx at the end of it? We usually see the dx or dy, depending on what variable we're working with. We usually see those at the end of an integration problem. And technically what they mean is the expression right before them is a derivative. So 1 over gy is the derivative of something with respect to y. And then f of x is the derivative of something with respect to x. So we want to go back to the original. Remember, when we solve differential equations, we're trying to figure out the original y function that's going to make that differential equation work. So now, once we get the x's and the y's separated, we're going to integrate both sides of the equation, because integrating will undo the derivative. Derivatives and integrals are opposite operations. And these integration problems shouldn't be very difficult. They should be pretty straightforward. That'll get rid of the dy and the dx once we do the integration, and now we'll just be left with an equation that has x's and y's in it. So if at all possible, once we get that, we want to, after integrating, we want to solve for y. Or whatever your dependent variable happens to be in that problem. Now, also remember back when we first learned integration, and we've been doing a lot of integration here in Chapter 7, if you're not plugging bounds in, then you're going to have a plus c. Now, we don't need a plus c on both of these integrals. We're only going to do a plus c on the side with our independent variable. So we only need that plus c on the x side. There's really no point in putting multiple arbitrary constants. And what we're going to get when we solve this for y is called a general solution. And the reason it's a general solution is because we still have this plus c in there. There is this spot where we have this arbitrary constant, which technically could create lots of different functions. For example, if we got y equals x squared plus c as our answer, technically that means x squared plus 2 will work, x squared plus 9 will work, x squared minus 5 will work. Putting any arbitrary constant into that plus c spot will still make the function work. It'll still make it a solution. So when we leave the plus c in there, We call it a general solution. So a general solution still contains the arbitrary constant. If we're given some extra information about our function, and sometimes we do know some extra information about our function, typically we'll know like a starting value. And in a lot of application problems, and almost everything we do in differential equation has an application that goes with it. In a lot of application problems, we will know the starting parameters for whatever problem we're working on. So we'll know like y of 0 equals 12. So I know at the start of my problem when x is 0, y equals 12. So if you're given some extra information about your solution function, such as an ordered pair or a point on the solution graph, then you can use that to solve for the plus c, and that will give us a particular solution. We call this extra information, we often call it an initial condition. An initial condition. Because in real world problems, very often the only thing we have control over are the things that we set at the start of the problem, and then once the other factors take over, and one example of a differential equation that that comes to mind is like projectile motion. We can think of that as a differential equation using gravity and velocity and things like that. You get to decide like the starting values of your projectile, but then once you shoot the projectile, you have no control over it anymore. The gravity is going to take over. So after that, we have no clue really what's happening unless we solve for the function. So they're called initial conditions because usually we'll know what's happening at the start of the function at y of 0. Y of 0 equals 5, for example. Then we can solve for that c, and it will give us a particular solution. We always have to get a general solution first, and then sometimes we stop at a general solution, but then we check to see, did they give me any more information about this function? If they did, then we can go one step further and replace our arbitrary constant and turn it into a particular solution. So if you're given some extra information about y of x, such as an initial condition, like y of 0 equals 5, then we can solve for the arbitrary constant and get a particular solution. But all the differential equations we're going to look at are going to be separable. They will all be separable. We will be able to write them in this format, dy dx equals f of x times g of y. We will be able to separate the y's to the left-hand side and the x's to the right-hand side, and then just solve by integrating. And then we just need to be careful of the instructions and see if they are asking for just a general solution where we can leave the plus c, or if they gave us some extra information about the function so that we can solve for the c and get a particular solution. So let's actually try a couple general solutions. So our instructions are to find the general solution of each differential equation. And we'll start off pretty easy. dy dx equals e to the x. So there's a couple things we need to think about to get this into the proper separable format. So remember, separable format is when we can get dy dx equals f of x times g of y. So we always want the dy dx alone on the left, so that's done. And then we want to make sure the right-hand side is written as a product of a function of x and a function of y. So right now we just have e to the x and there's no y's. And that's perfectly fine. We can always think of this as times 1 if we want to. And we can just say g of y equals 1. So this is separable. It does follow the format that we need it to. Sometimes we just need to be a little creative. So now that we know it's separable, it's in the standard separable format, we need to go ahead and separate the x's and the y's. Well, e to the x times 1 is just e to the x. We just need to make sure that everything on the left has y's in it, everything on the right has x's in it. In order to do that, all we have to do is multiply the dx over to the right. And we'll get dy equals e to the x dx. So everything on the left has y's, everything on the right has x's. And we can integrate. Now there is nothing inside this integral here. Remember we said that g of y could equal 1. And if you don't see anything inside your integral, we could always put a 1 in there. So we could think of this as the integral of 1 dy. So now we just integrate. So the antiderivative of 1 with respect to y is y. The antiderivative of e to the x with respect to x is e to the x. And remember, we put our arbitrary constant on the x side. And then, if possible, we solve for y. This one's already solved for y. And we were just looking for a general solution, which means we're not solving for the c. So we're all done. That's it. Y equals e to the x plus c. Now, it's probably one of the easiest ones you're ever going to see. They can get a little bit trickier. So dy dx equals 2x over y. Dy dx equals 2x over y. Now, if you remember our kind of standard form to confirm that it's separable, it said we would have multiplication on the left, and we have division. Division is perfectly fine. We can always think of this, if we needed to, as multiplication. Instead of dividing by y, that's the same as multiplying by 1 over y. It's the same exact thing. So we can write this as a product of a function of x and a function of y. We want to get all the y's on the left, so I need to multiply this y over to that side, and then I need to multiply the dx over to that side. So I get y dy equals 2x dx. And once we've got it separate, we will go ahead and integrate. So the antiderivative of y is 1/2 y squared. We just do the power rule. And then the antiderivative of 2x is x squared. And remember, we put our plus c on our independent side. Now, this is an example of one that I would not typically solve for y. If you remember back to algebra on how we would solve this, to get y all by itself, we would multiply the 2 over. If we do that, it's perfectly valid. We can multiply that 2 over, or multiply everything by 2. We would get y squared equals 2x squared. Now, one thing that gets kind of tricky, when you're doing algebra and there's an arbitrary constant, you don't need to apply like arithmetic operations to it. We have no clue what this c value is right now. Multiplying it by 2 still just makes it an arbitrary constant that we have no idea what it is. So we don't have to write 2c. It's still just plus some unknown value. Now we do have to multiply the x squared by it, by the 2. But c just represents some unknown value. It says x squared plus some unknown value. And multiplying through by 2, it's now going to be 2x squared plus some unknown value. The next thing we would do if we wanted to solve for y is we would have to square root both sides. And not only that, we would have to do a plus minus in the front. And this type of answer is really ugly. What you're technically saying is there's two answers. Y equals plus or minus square root of 2x squared plus c. So because of that really ugly plus minus in the front, I very often would not solve something that has an even power on the y. I would just leave that alone, and I would say this is my solution. Just follow what MyLabs Plus wants you to do. It's possible they'll want you to do the plus minus. I know we do have a plus minus button option on there when we're entering answers. So this is still true. This also works. It's just kind of ugly. So it leads to that plus minus in front. So I typically leave it as 1/2 y squared equals x squared plus c. Either one of them is perfectly fine. They're both correct. It just depends on really who is asking you to do it and what the specific instructions are. And I know that's very vague and probably not helpful. But if you do leave it, just pay attention to MyLabs Plus. The answer box might say y equals blank. Then you know they definitely want you to solve for y. Or if the answer box does not say y equals blank, if it's just an answer box, you might be able to just type the first one in, 1/2 y squared equals x squared plus c. If you get it wrong, make sure you read the box that pops up. It doesn't just say, no, this is wrong. It'll give you an explanation of what's wrong. Very often it'll say, although your answer is equivalent to the correct answer, we want you to solve for y. So if you ever get it wrong, make sure you read that the message that you get, because they'll usually tell you where you went wrong and what you need to go back and fix. So we saw one earlier where there were only x's on the right. Now I've got one here where there's only y's on the right. If you want to look at it as a product, you can say the x function is just 1, so that's perfectly fine. You can say 1 times y plus 2, so that you can actually see both of your functions. and we want to separate the x's and the y's. So I need to divide the y plus 2 over, and I need to multiply the dx over. Now this is a really important problem that leads to a very common solution. So now that we're separated, we're going to integrate. Now the antiderivative of 1 over y plus 2, you technically should write out a u substitution in order to do that, but it's going to end up as natural log of y plus 2. And then on the right, the antiderivative of 1 is just x, and then we have plus c. We are going to solve this for y. So just do your opposite operations until y is all by itself. The outermost operation is the log. So you got to think about what is the opposite of a log. What operation will cancel out a log? And that's an e function. So I can get rid of that log if I consider both sides of my equation to be exponents of e. Now you're not going to do it on each individual piece, you're just going to do it once on the left and once on the right. So on the left they cancel, because e to a natural log power, those are inverse functions, and all you're going to be left with is the y plus 2. And then now that we're out of the natural log, we don't need the absolute values anymore either. Now something is going to happen on the right, and I'm going to explain it as carefully as possible. Now we have addition in the exponent. The x plus c is now in the exponent. So when you add in the exponent, that means you must have been originally multiplying those two expressions with the same base. We typically do this in reverse. We typically are asked to simplify e to the x times e to the c and combine them. Well, if they have the same base, that means you can add the exponents, and it would be e to the x plus c. E is just a number. E is 2.71 something something something. Remember, c is completely arbitrary. So we said in the last example, doing arithmetic operations on c, we really don't have to change it away from just a regular old c. So this entire piece right here is still just a c. The major change though that has taken place though is it's not a plus c anymore. It was plus in the exponent, which actually makes it multiplication in the base. So we've got y plus 2 equals c times e to the x. I usually, c is a coefficient now, so I put it in the front. This is a very, very common problem in differential equations. It's got a lot of applications that go along with it. So it is something that we'll need to get used to. So the last thing we need to do to solve for y is subtract our 2 over. So we get y equals c e to the x minus 2. And that's our general solution. Now I'm going to show you one more that's very similar. Now I did not write out my u substitution on this one, but the next one's going to be very similar, and we do need to write out the u substitutions because it's going to make a difference in the answer. So just be really careful when you're doing these antiderivatives. Dy dx equals, I'm going to say x squared times 1 minus 2y. So it's already in the format that we know a separable equation needs to be in to recognize it as separable. And we're ready to separate the x's and the y's. So we've got to move over 1 minus 2y. We do that by dividing. I keep that separate from the dy because remember, the next step is integration, and typically with integration we see the dy at the end of the integral. It's not mixed in usually with the function. And then we've got equals x squared dx. And now that they're separated, we will integrate. This one also is going to turn into a log. Anytime you've got a linear function in the denominator and just a constant in the numerator, it's going to turn into a log. This one, though, you need to be careful of. I am going to write out my u substitution. If u is 1 minus 2y, du is negative 2 dy. So negative 1/2 du can replace my dy. So in this one, I get an extra coefficient when I do the integration. I didn't write it out on the last one because y didn't have a coefficient. So if I said u was y plus 2, I would just get du equals, I said du, but I wrote dy. Let me see. I would get du equals 1 dy, or du equals dy. It's a straight swap for the u's and the y's, and no extra coefficients are introduced. And the reason is because of the coefficient on the y. If the coefficient on the y is just a 1, then there's not going to be any extra new coefficients that come in. Here, the coefficient on the y is not a 1, it's a negative 2. So that's why we end up with this extra negative 1/2 in the problem. So just for the left-hand side integration, this turns into negative 1/2 integral of 1 over u du, which is negative 1/2 natural log of u, but we said u was 1 minus 2y. So we've got negative 1/2 natural log of 1 minus 2y equals, and then we need the antiderivative for x squared, and we just do the power rule. That's 1/3 x cubed plus c. And just like in the last one, we need to solve for the y. We can't do our little e trick yet because of the coefficient. So the first thing I want to do is I want to move the coefficient. The e's and the ln's only cancel if they're touching. So if I were to put an e here right now, the e and the ln aren't touching. There's something in between them. So we got to get the ln as the front piece. So to get rid of that negative 1/2 there, that's times the negative 1/2. To cancel it, I can multiply both sides by negative 2. So that ends up as negative 2/3 x cubed. And remember, we don't need to apply that operation to the c. C just means I'm going to add some arbitrary number. Multiplying it by negative 2, it's still going to be some arbitrary number. And now that we've got the ln in the front, I can consider both sides of my equation to be powers of e. And that will cancel my log. And once the log is gone, my absolute values can go away as well. Now I've got 1 minus 2y equals, now remember, plus c in the exponent turns into a c coefficient. And we just explained that in the last one, why that happens. When you have addition in the exponent, that technically means multiplication in the base, and e raised to an arbitrary constant is still just an arbitrary constant. The only difference is now it's multiplied. And we're trying to solve for y here, so we just have a little bit more algebra to do. We're going to subtract the 1 over. And then we're going to divide by negative 2. You really do not need to divide your c by negative 2. If c is some arbitrary constant, dividing it by negative 2 is still some arbitrary constant. So I've got y equals c e to the negative 2/3 x cubed. I had minus 1 divided by negative 2 is going to change it to a plus a half. So that's one of the trickier problems. That's probably one of the most tricky that you'll see in this section. So to finish up, what I want to do now is actually look at a problem where we're asked for a particular solution. And the start of the problem is exactly the same. The only difference is they're going to give us one extra piece of information about our function so that we can solve for the c. So we're going to find the particular solution. For the differential equation dy dx equals 1/2 x times y minus 3 if y of 0 equals 5. So now I know some information about my original function, and we can use that at the very end to solve for the c. We're going to start the problem off exactly the same way. We always have to get a general solution first. So don't worry about this until the end. So we're still just going to work with our differential equation, and we're going to separate the x's and the y's. I get 1 over y minus 3 dy equals 1/2 x dx. And then we can integrate. And that's going to turn into the natural log of y minus 3 equals 1/4 x squared plus c. And I'm going to go ahead and solve for y. So I need to think of both sides as a power of e. And remember, plus c in the exponent is going to turn into a times c in the front. And then on this side, e and natural log cancel. So now I've got y minus 3 equals c e to the 1/4 x squared. And then add your 3 over. Y equals c e to the 1/4 x squared plus 3. This is our general solution, and this is what we have been doing in our last few examples. But now we've got an extra piece of information about this general solution. I know y of 0 equals 5. Y of 0 equals 5 means that when x equals 0, y equals 5. Remember, x is the independent variable, and we always have the independent variable in the parentheses there. So we can plug those values into our general solution. So I'm going to replace y with 5. We don't know c, but the whole reason we're doing this is so that we can solve for the c. E to the 1/4 of x squared, but we know x is 0. Now the only unknown there is the c, and we just need to work it out. So this entire exponent is going to turn into 0, and e to the 0 equals 1. So this is 5c plus 3. If you subtract your c over, or 3 over, you get c equals 2. Now that is not our answer. We don't circle c equals 2. Our particular solution, we go back to our general solution and replace the c with 2. So our particular solution is going to be y equals 2e to the 1/4 x squared plus 3. We're able to solve for that C value because they gave us an extra piece of information about the solution function. So you still have to go through that whole process of finding your general solution. It's just a last little bit of algebra at the end to figure out the C value for a particular solution.